Okay, let's start. Again, I don't know what is happening with my OneNote, but now it's not letting me open the slides with color. But yeah, I really don't know why this is happening. Okay, so this is the last topic before the exam, which is really, yes, I think it's enough time for you to work the problems and come out with all the questions that you may have. Okay, so multiple lives moments. Last week, we defined multiple lives perspectives, right? Remember that here we have two approaches. We have A, joint life, and B, last survivor, okay? Fails with the first death. No? So essentially, this is a big difference between these two. One is going to fail when the first person dies, and the other one is going to fail when the last person dies. And we also saw that given, if we assume independence, we know that this equals the multiplication of individual probabilities, and also for forces of mortality, we are just going to add them, and for last survivor, this, okay? So this is essentially what we learned last session, and these are things that we're going to use now, but to estimate life expectancy, well, joint life expectancy or life expectancy for life survivor, and moments that we probably want to estimate for these things. And let's use some interesting approaches. So the first thing that we're going to discuss is expected values, then variances and covariances. Again, it's not something that we're going to discuss in detail, but actually I think it should be the other way, because we're going to spend a lot of this session working with the special distributions that we know that are really convenient for us to find that the future lifetimes follow these distributions. And then at the end of the session, we are going to discuss what happens with variances and covariances, okay? And that's the session plan for tonight. So to estimate the first moment or the expected value or the joint life expectancy or last survivor life expectancy, in both scenarios here complete, but it should be the same with quartate, we have the following. Again, since we just need to integrate the probability here, this is the same as if we can have the individual probabilities and then just work the multiplication is just essentially algebra, and then integrate for the time that we need to estimate this expected value. For last survivor, again, we can estimate this if we want if we have the expression for last survivor, or we can also remember that since we can split this probability into individual probabilities, and then subtract the joint life. Well, and then I'm missing the differential of t there. So we can do it in both ways. And again, if we want just the temporary, this would be, and here is when these things start getting interesting. So this is the temporary complete joint life expectancy for these individuals. So it's a lot of information in this thing, But again, it's nothing different from what we did before, just using the interval between 0 and n. And we could also have the last survivor, the n years temporary complete last survivor life expectancy. Yes. So again, we can have all these things in these expressions. It's not different from what we did before, but now we have to take into account that we have more individuals in our population. Okay. So let's start working some examples so you can see how these things work. Okay. And this is also a good checkpoint just to see if you have things fresh in your brain, in your memory, with all these things that we have been doing. Okay, we have two independent lives, a person age X and a person age Y, and we know that the force of mortality for X is 0.01. So for any value of X, that's the force of mortality, and the force of mortality for Y is 0.02. Let's estimate the expected time until both die, essentially to the last death of these two individuals. So what we want to estimate here is this, okay? So I'm gonna help you with the first part, which is really easy. Now, how are we going to estimate the life expectancy for X? No, we don't have to do that. Remember, when mu xt when we have constant force or mortality, the expected value is this. We did that for one life. And now it's raining here, so if I'm kicked out of the session, please wait for me for a few minutes, just to make sure. Okay. So when we have constant force of mortality, it's really easy. We don't, well, okay, if you want to integrate, that's fine. But again, we can solve this, and this is a good question, and this is a good example of questions that you may probably you can find in SOAS exams. So they will give you this, and you have to remember things that you already know. So this is 1 divided by force of mortality for X, 0.01. Then 1 divided by force of mortality for Y. And what happens for the next one? Exactly. Because we know that if we want to merge two life expectancies or two forces of mortality, we just add the two forces of mortality. But then, since they are constant, the new joint force of mortality is going to be constant, so the life expectancy is going to be 0.03. Is that clear? And how much is this? Okay, we have two different values. I need a third opinion in these things. Okay. Ah, thank you, Lupita. Lupita is paying attention. Now, yes. So I'm guessing the one Lupita is correct. Mhm. Okay, so of course, in the exam that we will have is not going to be as easy as this, but again, this is just being practical. Okay, so the force of mortality are constant, so I can just get the expected value or the life expectancy as the reciprocal of the force of mortality. And then just remember that if I want to estimate the joint force of mortality and I have the two individuals, I just need to add them. Again, these are things that is just practice and practice and practice. Okay, so let's move to a more interesting, more interesting things. Okay, so we have, remember that we have the Moivre's law. Essentially, what we have in the Moivre's law is that the expected value is omega and then subtracting the age that the person has and then divided by 2. And this, again, it makes sense that if we have the age limit, let's say that we have omega of 100 and x being 50, that the expected value of this person is going to be 25. Why? Because we already have 50 years live. We have 50 more years to live. Some people will die right away, and some people will die right before 100. So the expected value is just the midpoint in this distribution. And again, this is just a uniform distribution, which probably makes more sense when we see the variance. Okay. Now, I think I call it beta in the verification problems, but again, we can also see this as a generalized Moivre's law. And this happens when we have a parameter different from 1 here. And again, this would be the force of mortality when we have that scenario. And the expected value is omega subtracting x. And here we are going to divide, the division is going to be using the parameter plus 1. And the variance is, again, it's just a longer formula, but it's really straightforward to estimate. Okay. And let me see. Yes, I think this is what we have here. Okay, and I think something that I need to include here. And for this generalized map, like that. Again, these are formulas that you should probably have next to you for the exam because they're going to be really useful. And you're going to see now when you start working with in the verification problems for this part that these are things that is better if you have them with you. Okay, so let's see what happens when we have the Moivre's law of mortality. We have two independent lives, essentially some person who's age 40 and somebody who's age 55, and we know that again both of them follow the Moivre's law of mortality. The first one with a value of omega 100 and the second one with a value of omega 115. Let's estimate the expected amount of time until the last death. Again, this is, since we want to estimate this to the last death, is a last survivor, and this is the one for 40, and for 50, and then subtract the joint life. It's 55, right? Yes. Mhm. So according to what we had before in the previous slide, since I know this follows a law of mortality, this is omega, which is 100, subtract the hx, divided by 2, which is 60, 30. Mhm. And for this next person, omega is 115, 55, 2, and is the same, 30. Mhm. Now, what happens with the joint life? Mhm. So joint life, essentially, if we estimate, so for either life that we have, let me go back to this previous. Mhm. I don't think I have here. Yes, I probably should also include this. So the force of mortality for this, for omega, well, for the mass, sorry, is just like that. So this is the general expression for the MOABs when we have, not the general expression for force of mortality when we have the MOABs law. Okay. So this is interesting because here the two individuals or the two persons essentially end up with the same expression for force of mortality. Okay. Which is 1 divided by 60 and then subtracting t. I don't want to be lazy. Let me write the complete expression. Which is equal. Just because in this scenario we have the same distance between omega and the edge of the person. Which is really convenient because this means that the force of mortality for this joint life status is going to be 2 times 16 subtracting t, which is not longer at the more low mortality, but this is a generalized remarks. With the parameter alpha being 2. And again, this is something that we can do because what we know is that then the expected value for this is going to be 60 divided by 3, which is 20. Now, here is like I'm not even using 40 and 55. Essentially, here is just like having a new, if you want to call this the new edge or whatever. So I can use this generalized Marx expression. But again, because somebody was asking me in the previous section, okay, so that means that x is 0 or y is 0. No, no, no. It's just that now, because it was convenient for me, I ended up with something that looks like a generalized Marx expression. And remember that this is just notation that we have. And we know that the expected value for this is just the distance that we have between the h and omega, and for the two of our distributions is the same, divided by the parameter plus 1, so it's a 20. Okay? So this means that this life expectancy is 30 plus 30, 40. You see, so it's really convenient to remember these things. And again, you're gonna gain like speed with these things. probably by the time that you are not going to need them anymore, because we're going to change topics really soon. But again, it's really convenient to have these things. And again, it's not that we're going to forget about the WAPs, but again, we won't be doing these things by hand all semester. Okay, so questions here? Okay. Wonderful. So in this scenario, it was really easy because we ended up with having the same distance between omega and x and omega and y again. So it was convenient. But what happens when we don't have that same distance? Hmm? So essentially, this is what we had. Okay. So these were the same. When this doesn't happen, which is going to be a lot of times, right? When we won't have these exact values, we still have a way to generalize the expression. So let's find a general expression for these things. Okay? So for this, come on, let's see. A, this. Essentially, I'm making this A and this B. With the big condition, and this is the important thing, that A is less than B. If they are equal, we're in the previous scenario, right? When we can just add and move from the marks to a generalized the marks. What happens if the distance for omega x and x is greater than omega y and y? Then we just switch. We just make the second person x and the first person y. Again, we just need to identify the one that is closer to the h limit. Okay? So based on this, we have then the probability of surviving from hx to hx plus t. Remember that this is omega, which translates into a divided by a. And similarly for the second person, that would be subtracting t divided by t. Now, for the joint status, essentially what we have is that the expected value or the life expectancy for these two So here the limit is A, because since A represents the group that is closer at the distance between x and omega x is the one that is smaller, it only makes sense to go all the way to A, right? Because again, after this would be 0, 0, 0, so we will end up. But we will start adding zeros to this life expectancy. So that's the reason this goes all the way to A, and because of this assumption. I'm just moving this constant out of the integration process, and I'm gonna get really creative with this integral because I'm just going to add 1 0 here. I'm not going to skip any steps. So I'm just rearranging everything inside the second parentheses. So this is convenient because then I can just multiply a minus t times this part of the equation and then times the second part of the equation. So I'm just being creative here because I don't like really long uh, integration processes. I think we can, yes. So let me, and again, you can replace this, but that you should reach expression like this. Am I missing something? No, I think I'm fine. Uh, well, I think I shouldn't probably have done that because I think it would be easier to split this b. Yes, I think it would be easier to split this or to multiply this b times a squared divided by 2, and then we will end up with 3. Yes. I don't think this is the best way to. Well, I know the final expression, but I don't want to just jump to that final expression. No? No, this is 2. Huh? I think I need to move to a new page. Let me write again the previous one. So it was uh, I got tired. So I'm just gonna write the final expression. But you can reach this expression from this fact. Again, if you want to get this difference, so that's the reason you get this 6, and then you get the square because you get rid of this a here, and then the b should be around there. Okay, so this is the like kind of the final expression that we get if you work some algebra here. Now we can replace A, which was this, and B, essentially x equals let me replace B. Now this is clearly this value here. Now here we kind of have the square value of this, but we're missing 1/4. So again, I can adjust for that if I just multiply and divide by convenient values. But let me just write the final expression. So this is the general expression that we can use to estimate joint life expectancy when the differences between the age limits for X and Y are not the same, taking into account their age. I know probably you're going like, this doesn't look really easy, but trust me, sometimes it's better to use this expression than going with the long approach to getting the probability and then work all the integration process. It's a time-saving, essentially, approach. Okay? Okay, so let's see how this actually works when we have one example when these distances are not the same. Okay, this is actually pretty similar to the previous one, but now instead of having 115, we have 105. So of course, this is going to change the way that we do it. Okay. So, and now I am getting creative here in what I am asking for. I am not asking you for the life expectancy for the last of the two deaths. I am asking you to the expected amount of years of time essentially between the two deaths. Okay. So essentially, in order to answer this, we know that this one is giving us time to first death, and this one is giving us time to last death. So essentially, the answer that we are looking for is this difference. Which again, we can write as as this. Hmm? It is really raining. Hmm? And that is coming from a guy from Tabasco who knows rain. Okay. So the life expectancy for X, and let me write ages now. For E is omega, subtracting the age for E divided by 2, which is 30. Okay. Now for the next person, this was when we changed the value of omega. So 105, subtracting 55 by 2 is 50, so it's 25. Okay. So now we need to estimate to find the joint life expectancy. But now we have the following. Omega 40. I'm just gonna use 40 because I just wanna to make clear that this is not X all the time. So the smaller, the closest one to the age limit is the second one. So this is going to be B, sorry, A, and this is going to be B. So let me go to the next page. So A going to be 105, 50, 60. Here we can tell that A is actually less than B, which is fine. And this is the important thing, because even though I have been calling the first person X all this time, the second person Y, for this join, essentially what we're going to do is that X is going to be the person who's age 55 and Y the person who is age 40. Because we need to make this distinction in order to be able to use this formula. Okay, so this means that the force of mortality for Y essentially is 1 divided by 60. Omega subtracting the age 60. Now, we can use our formula. And according to our formula, the expected value for xy is expected value for x, and subtracting 2/3 of the expected value for x squared, and then times y. So the expected value for x is going to be 25, then 2/3 of 25 squared times 1 by 60. How much is this? Thank you. Which means that the answer that we were looking for, which was 40, 55, 55 was, I don't know, it was 40, 5, Hmm? Which is 30 plus 25. Hmm? Thank you. Okay. So here the important thing is just be careful on who's X, who's Y, but then when you go to the joint life expectancy, it doesn't matter, you can switch them just in order to make sure that A is less than B, and then you can use this formula like directly, which I think is something really convenient to have. Okay, questions in this example? No? Okay, so we can move to a more interesting example. Okay, this is something more like applied, we can say. Again, here we have a population. In this population, we have smokers and non-smokers. Okay? We know, or we are given this following information. Non-smokers have a force of mortality which is equal to 1/2 of the force of mortality of smokers. Okay? And now, and we also have the survival or the survival distribution for non-smokers, which essentially is expressed as 75 subtracting the age. Which again, this is a different expression for a demoived mortality. Okay? If we just plot this, we will have a straight line. With omega being 75. So we also know that 65 is a non-smoker and 55 is a smoker, and they're independent. So let's estimate the joint life expectancy for these two. Okay. So what do we have here? So we have for non-smokers based on this. So from here, we know that for non-smokers, smokers with omega being 75, the probability of a person age X reaching age X plus T is 75 subtracting H subtracting T divided by 75, which is the general expression for our demoived low mortality. Okay. We also know that if this is the expression that we have for the probability, we can get force of mortality for these people, right? Which is going to be 1 divided by omega subtracting x. Again, we know that omega is 75. I could just write here 75. That's fine. So who can tell me the value of force of mortality for Y? Let me make Y non-smokers. Sorry, X non-smokers, Y smokers. Exactly. This would be 2 divided by omega minus x. So here on purpose, again, this is not my example I get it from a book, but it's not that I'm playing with you, but it's important to see what we have. Here we have the distribution for non-smokers, but the information that we have is that this is half of this. So here we have to work like backwards, essentially first estimating this force of mortality, and then just double this force of mortality in order to estimate to get the one for smokers. So this is the MWAP, the one we have here, and this is a generalized MWAP again. This is really with alpha being 2, which is really convenient because from what I wrote in a previous slide, what we know is that the probability for y is going to be 75 and now we can estimate the joint life expectancy. Okay, this means that the joint life expectancy for 65, 55, so this is going to be long. Right, and then you can just solve this thing by any mean that you want to solve this thing. So because I am lazy, I just hate having really complicated integral expressions. I would just add this. I have here the square value of this is 400 then times. So we're going to do something like this. And again, you can work some substitution. You can do whatever you want. Here, because I am really lazy, I would just develop all these things because for me it's really easy to get the integral of t squared to whatever thing. And again, I can just, that's a really easy thing for me to integrate. But again, if you are better with substitutions, go with that. But again, I'm not going to spend a lot of time here, but I can tell you, and you can practice these things, these results in 417. Again, the important thing here is to see what we have, what can we write in terms of what things we have at hand, and then just being creative on the way that we can essentially solve this using the maps. Again, you're gonna find lots of the maps because that makes things easier. Next session, we're gonna start working with some life tables so you see how these things apply to life tables. But again, the general idea is the same. Okay, I think I had enough things, well, the slides for that interact. Okay, now let's talk about variance and covariance. Because now we have more than one person. So if we were to estimate the variance, this is the general expression that we have before, and this is just one way to see these things. So this is the expression for variance when we have 2 persons in our population, and it's just making essentially adjusting for the things that we had before for one life, which is really not that ugly, at least the variance. Now, what happens with covariance? So we had the assumption that these two lives were independent, which again is something that we know. So what happens with covariance when they're independent is that essentially this does not exist, right? It goes to zero. However, we still have this other part, which is the consequence of the way that we construct these expressions. So we end up having the covariance for this joint life being this thing. So again, it's more, I haven't seen one instance when they actually ask for covariance, because again, it kind of loses meaning on what we're doing. So we usually are paying attention to the expected value and the variance, and those are things that we can essentially estimate without any problem. But look what happens. This is for joint life. If I were to estimate this for last survivor, it would be essentially the same. But now here I will end up with this. Which make things a little bit more time consuming. So most times when we have more than one life, we will only pay attention to life expectancy. And yes, sometimes we can actually estimate the variance for these things, but it's not that common. Okay? But again, if we want to, we can estimate the variance. And again, but there shouldn't be any problem for us to estimate these things. Again, it's just being careful with the limits that we're going to use for the integration approach, and then estimate these things. Okay, so this is because an offer that I just made to the previous section, and I have to make this offer to you as well. So this is going to be something that you have to do, or at least try at home. You have to submit this before the next class. Even if it's 1 minute before the next class, that's fine. But you have to submit it before the next class. Okay. I will not give you the answer because I need to use the same. I need to offer the same opportunity for those in the sections that where we have class on Tuesdays and Thursdays. So I will give you the answer on Thursday after everybody has submitted this thing. Okay, so it shouldn't be that complicated because we have persons the same age. So some things are going to go away, or we can group certain aspects. But this is a good example of a good thing that you probably should work in order to get familiar with these things. And it's for at 1 point in the first exam. Okay, questions? 1/10. I am being really, 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 really nice. But okay, let me